pleasure to welcome Bob Sedgewick, Robert Sedgewick, but in the analysis of algorithm community is known as Bob. So Bob did his PhD thesis under the supervision of Don Knuth in 75, I believe. And since he did a lot of seminal works in the analysis of algorithms, and in particular uh, sorting algorithms, divide and conquer recurrences, and also some online algorithm, perhaps like he will talk about today. He wrote a lot of influential book, I would say, in computer science, like the series of algorithms in C, C++, and so on. But for going to books which are a little bit more advanced, he also wrote the nice book, which was an introduction to the. Oh, I was checking if I have it here, but okay. The introduction to the introduction of algorithms with Philippe Flageolet. It was 30 years ago, and then later they did well, the Bible in your field, which is analytic combinatorics. So I think that we will have a taste of this in his talk. Bob did also a lot for the community, organizing conferences and so on, but he did also a lot for contact between computer science and the business world, I will say. So I believe he was in the board of Adobe. I'm not sure what is the full official name, Adobe Systems or something like this for more than 20 years. So we have a true computer scientist, and Bob, I leave the floor to you to check what a true computer scientist can say on the links with applied mathematics. Thanks.
Okay, thanks. This talk is like a combination of a survey and a presentation of new results. And yes, there's some computer science, but there's also, you'll see the math plays a really critical role. This is dedicated to the memory of Philippe Flageolet, who I worked with for many years and actually plays an important role in this story. So first I'm going to talk about something called algorithm science. So that's an approach to studying algorithms where we embrace the scientific method. And just a short history, when computers started, figuring out what they're going to do, what kind of resources they're going to use was very important. And Turing and von Neumann and Hoare and many others definitely took this approach. Knuth wrote a series of books in the 70s and 80s that really developed the idea. And my books in the 90s and 2000s popularized it. And really, there's an argument that this approach enabled the development of the computational infrastructure that we have. A lot of our code is tested. We have mathematical models that describe what they're going to do, and then we test those models with validating hypotheses about how they perform in the real world, and then people adopt them. So, my code for quicksort and balanced trees and so forth is in your phone and billions of other devices. One interesting point, like for the present and the future, is that Moore's law is almost over. So people can't rely on the computer just getting faster. Actually, we're going to have better understanding of what the algorithms are doing. And the only way to do that is to have appropriate mathematical models. And this talk is an example of that. So the basic idea is we start with a real program that we're interested in, and real data that we're interested in having the program run on. And we want to develop a model of what's going to happen. Most often, how much time is the program going to take for that kind of data? And then we use that model to formulate some hypotheses about the performance. And most importantly, there's usually parameters, and we want to figure out the values of the parameters and tune them. And then we do experiments that are at least supposed to like model the real world. And that gives us an opportunity to refine and iterate. So this is the cycle of the scientific method. And I know I'm talking to mathematicians, but I think this is a really important aspect of our work. What we do is experiment to validate hypotheses. Sometimes we're wrong. And so then we have to start over again, but most often we're able to improve things. And so the problem that I'm going to talk about today is really a prime example of this. So the problem is called cardinality estimation. And this is a really fundamental problem in data science, has been for decades. So you want to know, you have a stream of data values coming in. You want to know how many different values are there in there. So the reference application is, so this is a web log. And you want to know how many unique visitors there were in a day or a month or a minute, depending on whatever your application is. How many of these strings are different? And I have a test file that's got 6 million strings in it. And there's 6 million strings. There's not that many that are different. So for decades, the way to solve this was just sort and then just go through and count, because when you sort, then the equal ones come out together. So like in Unix, you can just say sort minus u, that file, and it tells you out of the 6 million, 1,112,365 are different. And in the database, SQL, and many modern things, there's also like primitives to do this. You can do faster than sort by using a hash table, but the problem immediately becomes that you have a stream that's much too big to fit all the values in memory, so you can't sort them. So what do you do? And I'll give some numbers in a minute to make this clear. So what we want to do is estimate the value, and this is what I'll call the practical cardinality estimation problem. You only get to make one pass through the stream. It's something that's flying through your computer, and you only see it once. You want to use as few operations per value as possible. The algorithms that I'm talking about are used in, for example, network switches, and so you don't want to slow things down by doing this job. You want to use as little memory as possible. There's lots of these little devices, and you want to use them, and you want to get an accurate estimate. So that's the problem. And there's lots of applications where you don't really need the exact count, but you want a good estimation. Like I just said, how many unique visitors to my website, how many in a database, how many different things are there, how many different IP addresses hit this node, and even real world things like traffic planning. And so just to get an idea of the scope, nowadays we think about billions of streams, each having trillions of values. So there's no way that you want to keep the memory down because there's lots of them, and there's no way that you can see them all. And so the question is, how much memory do you need to estimate the number of distinct values within, say, 10% accuracy? And the answer is it's way less than you might think. It's kind of surprising at each stage of the development of these algorithms that I'm going to talk about. So the this research on this has been going on for a long time, and it goes back to 1983, and that's Philippe Flageolet and Nigel Martin developed an algorithm called probabilistic counting. And they were very excited to Martin was very excited to get an algorithm that seemed to work for him. His application was databases, but he couldn't really properly tune it until Flageolet came along and gave a mathematical model. But this is over 40 years ago now, and they introduced really the field of data streaming. In about 15 years later, there was a theory paper that put this whole idea of streaming in a theoretical framework, and that led to lots of, I call them theoretical results that didn't have that much impact on practical computing. A little bit later, Flageolet went back to the problem and improved his first algorithm in a method called log-log counting, and refined that in a method called hyperlog-log. And I'll talk about these algorithms. So that's 2007. That's almost 20 years ago now. And people have tried lots of different things. And then what I'm going to talk about, uh, all of this is described in a paper by Jeremy Labroso in 2013. And then what I'm going to talk about today is an algorithm that we presented last year at A of A. And so that's 40 years of history on these algorithms. Uh, and as you'll see, the math really plays a critical role in this. Okay, so let's talk about the solutions. So these are the methods developed by Flageolet over the first, say, 25 years of this research. And these are all great papers, really worth reading. So the key steps are the following. First, we do what's called hashing each item. And that's a standard thing in computer science where you take your items and you perform a computation on them, and what you get out looks kind of like a random value. And then we're going to call the amount of memory or the memory we use, which is called a sketch, and that's going to enable the estimation. Uh, and then what we need to do to get accuracy is to split this stream into m substreams and record the estimates of the m substreams, and then average them, and then analyze the bias that you get from this process. And it's the analysis that I think is going to be of most interest to this community. Now, the probabilistic counting, the sketches were M 32-bit values, and log, it got it down to 5-bit values. I'm going to update that to the 21st century. And really now we have to think about 64-bit values or 8-bit. Anyway, that's a little detail that is very important to computer scientists, and I hope it's not too confusing. Okay, so first step, hash the values. So this is hashing was used in the 50s, 1950s, and it's been very effective since, and it's used in lots of applications. And the point is, if we use a 64-bit value, we're not going to, we have a very low probability of affecting the, extremely low probability of affecting the cardinality count. And it's all built in modern systems. It's people have known how to do it with just a few machine code operations for many years. So I don't want to talk about that technology. It's called the Mersenne twister, and it uses a few machine code instructions. And so what it allows us to do now is think of cardinality estimation on streams of binary integers, not arbitrary strings or whatever else the items might be that you want to count. So we think of these things as random, that the hash function produces each value with equal probability. But some of the values might be equal because we're starting with equal things, and the hash functions are deterministic. Okay, so next step is focus on the trailing ones. So we're going to let X be the maximum number of trailing ones in a random stream of distinct binary values. So start with a little math. The probability that no value has k trailing ones is 1 minus 1 over 2 to the k to the n, and that's about e to the minus n over 2 to the k. So probability that the max number is greater than k is simply 1 minus that. And if we just take a minute to look at that, if k is small, that's really close to 1. If k is large, that's really close to 0. And the expected value of the max number of trailing ones is summing those. So that's kind of that's the plot of 1 minus e minus n over 2 to the k. And so it's about log n ones and all the rest are 0. There's some in the middle that are not close to either 0 or 1. And with just this quick sketch, you can see the expected value of the max number of trailing ones it's about log n. It's a little bit bigger than log n. LG is log base 2 for computer scientists. Okay, so now what we want to do is perform M independent experiments. Now, we don't want to use different hash functions. That's too expensive. And we don't want to alternate, just take 1, 2, 3, 4, 1, 2, 3, 4 like that, because that'll produce bad results for certain inputs. So the idea that Flageolet and Martin came up with is called stochastic splitting, where we use another hash to divide the stream into independent streams. And the key idea is then that equal values all go to the same screen. Sorry, I didn't mean to throw that away so soon. Because the second hash will route the equal values to the same stream. So it really gives the independent experiments that you want with the second hash. Okay, so now what we want to do is average and analyze. So the log-log algorithm, it takes the arithmetic mean of these values. And the paper proves the bias is 0.794, and it actually also computes the standard error precisely. And again, it uses 8M bits. And then hyperlog-log, which is a refinement, uses a geometric mean, and it gets a little bit a different bias and a much better standard error, and the same amount of memory. So this is what the code looks like, and I know it's mathematicians, but this is really simple code, and it's just summarizes the ideas in code. So we use M sketches. They're each 8-bit bytes. Compute the hash for every string in the stream. We compute the hash function, and we compute the second hash function to figure out which substream to put it to. And then we just test. We have a function that computes the number of rightmost ones, and that's actually really easy to compute, it turns out. And we just keep track of the maximum, and then after that, we just average them and return this bias factor times M times 2 to the mean. So that's the whole algorithm. It's a very simple algorithm, not very much code. But there's some critical questions in here that are a little bit masked. Where's that 0.794 come from? And can we characterize the accuracy? And folklore says that, and Philippe always said this, but we haven't found it in print. Without the analysis, there's no algorithm. That is, where did you get that 0.794, and what's your model for the accuracy? And that's a key factor in this. And people might think, well, actually, all the way back, Martin, he had an algorithm like this, and he just ran it, and you can run it a lot of times and empirically determine a value for this constant. It's a little bit harder to empirically figure out the accuracy, and there's parameters. You want to know how to set the parameters. You want to understand it. And people might think, this is an average. It's simple, and these papers are worth reading to really understand this. And this is an old derivation that many people are familiar with. But if you're not familiar with it, it's kind of amazing. So anyway, in the log-log paper in 2003, they proved these explicit formulas for the expected value of the estimate of the cardinality and the standard error. And there's this thing about small oscillating functions of magnitude 10 to the minus 6 that I'll talk about in a minute. I'm leaving out the assumptions on the hash function, and I'll talk a little bit more about that in a minute. And the proof sketch is pretty standard nowadays. It formulates it with a generating function, uses a Poisson approximation. There's melon transform, which helps uh, compute which helps us get to the average value. And so this is standard. I'm not going to go through this proof, but I just want to talk about the result to convince people that you're not going to get here any other way very easily. So the fact is that you have to know about the gamma function in the complex plane in order to be able to characterize this magic constant. So this is, classical results about the gamma function, uh, and involves Euler's constant. So we want to know, since this is just for m equals 1, what's the maximum or leading zeros in a stream of random values, n of which are distinct? And the answer is it's the sum of the residues of this function, gamma z n to the minus z, 1 minus 2 to the minus z, at its poles. And so that is the first part is the estimate quoted for the mean, log n, with the correction gamma over log 2 plus a half. But there's this other additional term, which involves the evaluating the gamma function along a line in the imaginary axis. It turns out that these values are extremely small. There's actually more. There's uh, another term of magnitude 10 to the minus 12th and then 10 to the minus 18th and so forth. But that's the answer. So you're not going to prove that it's asymptotically equal to this first value because there's oscillating functions involved. And so I like to say, Philippe says without the analysis, there's no algorithm. And I like to say without the gamma function, there's no analysis. And it's actually, the newsflash is it's actually not a constant, which is very surprising to many people. And actually, Ramanujan and Hardy knew about this, and there's a long story about that too, that Cyril's more familiar with than me. Okay, so what we really need is not just the average value, we need the distribution. And so this method was developed in 1973 by Knuth and De Bruyn. But later on, we found that the method generalized and we found lots of applications. And then Jacquet and Spankowski introduced this idea of Poissonization that allows approximation of the full distribution. And so Duran and Flageolet analyzed the distribution, which you really need to characterize the trade-offs. And the question is, what are the essential characteristics? And the answer is it's approximately normal with that quoted standard error. So that's the math, and I'm not going to give this full derivation because I'll give a different one, or at least talk about a different one in a few minutes. So now what we want to do is, that's our mathematical model. Now we want to create a hypothesis about what goes on in the real world. So there's a fact is that hash values aren't random, it's deterministic. There's no such thing as random in a computer. It's all deterministic. So our first hypothesis is that whatever hash values we use, whatever data we have, are going to be sufficiently close to random that our model works. That's our hypothesis. And so if you're using hashing, you have to run experiments to validate any hypothesis about performance. And again, that's for no problem for us. We always validate hypotheses in algorithm science. We have the algorithm. I gave you the code. We're going to run it. And we're just trying to understand how it works. And what we want to do is develop algorithms that are useful in practice. And it's no good to just say, oh, I think this algorithm might do that. Before you put it in an algorithms book, you really should have some validation that it's going to work. And by the way, it's extremely rare to discover a performance problem due to hashing. I mean, there are examples of really bad hash functions, but those went away decades ago. And to discover a performance problem due to non-randomness in the Mersenne twister would be an amazing result. Uh, so again, we run experiments to validate hypotheses. So in this case, our turning that theorem into a hypothesis is really the way to do it. It's saying uh, uh, and we're going to expect that the cardinality estimate will have this value 0.794 with a standard error and that it's normal. And I should even take off that ignoring small oscillating function because you're never going to see that. When I first saw this problem, I thought I could maybe run experiments to show the oscillation, but no, it's way too small and you'd have to I still don't think you can do that. So anyway, this is a hypothesis. It's not a theorem. It rests on some assumptions about the existence of truly random bits. And any program that uses hashing is going to have the same thing. For example, say I want to estimate n to within 10% accuracy 95% of the time using thousands of bits. And the hypothesis is that log counting does this with about 6,000 bits. And just doing the math, you get sigma within 2 sigma 95% of the time. That's what you think. So that's the real hypothesis is we're going to be within 10% accuracy 95% of the time. And so this is an experiment where I do 100 trials up to 1 million, and I do every 10,000 inputs. I do 100 trials, so there's 100 dots on every vertical line here, and there looks pretty good. They're within 2 sigma 95% of the time. Or if we just take one slice and we do 10,000 trials for 1 million inputs and then do a histogram of the value return, it looks pretty normal around the actual value. So I consider that a validation of this model and this algorithm. And uh, so with that, so that's a hypothesized distribution. Again, hyperlog is all different math because it's a geometric mean, but still it's got a similar kind of hypothesis and result. So this is 2018. This is an example of so this algorithm's been used for decades now by lots of people. And, people come up that don't know about it. So this is 2018, where somebody's trying to count the number of distinct people that used Facebook in the past week. Well, they used SQL, that thing that I showed like 50 years old. I don't know what it's trying to do, but they realized that it might take days and terabytes of memory because they would have to put them all in and sort them, and God knows what they would have to do. So they implemented hyperlog, and they figured out that actually they can do the same calculation in 12 hours within 1 megabyte of memory. So that's improving things by a factor of 1 million. So that's a good day for algorithm science. So once you learn hyperlog and you have this application, you're going to use it. And these are all kinds of people using hyperlog now. And even Amazon announces hyperlog, which is like amazing. Like it's like a 12 line Java program, really. But that's an example of practical impact of good algorithm science. So now the question is, can we do better? The first one, probabilistic counting, I didn't talk that much about, but it's similar, but it used 64-bit words. And log counting and hyperlog is a big improvement in the amount of memory because it just uses 6 or 8-bit bytes. And the optimal would, I guess, be 1 bit, although that seems like a stretch. But anyway, that's what we're left with at this point. And so that's what I'm going to talk about next is the more recent algorithms. Can we do better? And the answer is yes, we can do better. And then now I'll talk about our paper from last year at analysis algorithms in Bath. Okay. So anyway, so our goal is to optimize the use of memory. So this is the summary for hyperlog. And so our optimal algorithm that we're trying to invent, what we want to use is 1 bit per stream. We don't know the algorithm, we don't know the bias, we don't know the standard error, but that's what we're trying to get to. Okay, so this is kind of it took me a long time to get here, and I'll talk a little bit about that. But here's a really simple algorithm that does this. So we're going to start with a rough estimate T of the number of distinct values per stream, the log of the number of distinct values per stream. And then so we now have M substreams, and we're going to compute the fraction of the substreams with no values having more than T trailing ones. And we're going to use that to estimate N over M, to use 2 to the T to estimate N over M. And we have to find the bias factor. Well, the bias factor turns out to be log of 1 over beta. And that's an extremely simple algorithm. It uses so M is the number of streams, T is the estimate of log of N over M. And now we have an M bit sketch. There's no such thing as a bit array in any programming language, but it's easy to implement and it makes the code a lot simpler. Then we do our 2 hash functions, and then we just check if the number of trailing ones is bigger than T. And if it is, we set the sketch to 1. And then we look at the fraction of in the sketch that are 0 that didn't have T trailing ones, and then just modify it by that log 1 over beta. And that's an extremely simple algorithm. And I won't talk about the computer sciencey parts of this, but this can be implemented in a few lines of machine code. So it's that simple. Okay, so I want to talk about the computer science parts of it. Now, this only works when T is close to being right, but it turns out that it's not that sensitive to the value of T. And that was a big discovery that took me years. So let's just do a elementary mean value analysis. So if the number of zeros in the beta is a fraction of zeros in the sketch, if the number of zeros in the sketch is M beta, what's the expected number of values, distinct values that have been found? Well, again, if you have V distinct values, the probability that a given value has at least T trailing ones is 1 over 2 to the T. And the probability that no item has at least T trailing ones is 1 minus that. Again, it's e to the minus V over 2 to the T. And after so this is a binomial distribution. And so the expected number of zeros in the sketch is M times that probability. And so the algorithm is going to terminate with the expected number of zeros equal M beta, and that gives a value for the number of distinct values, 2 to the T log 1 over beta. That gives the correction factor. So expected number of values is M times 2 to the T times the log of 1 over beta. So that's the mean value. That gives us the magic constant. So we have an algorithm, but we want it's a distribution. And the similar kind of proof, but this time I asked a probabilist, Svante Janssen, who came up with the proof that the distribution of the number of values is asymptotically normal. And gives explicit expression for the standard error involving this constant that's a function of beta. And that's an interesting constant. Study this graph for a little while. If if beta is close to zero or close to one, it's too big. But there's a big range where it's relatively small, like less than 1.5. It's explicit, so it's a model that we can work with when designing algorithms, as you'll see. The one thing that this tells us is that the range of reasonable accuracy depends on our two parameters, but it's quite large. So if we say we want the standard error to be less than 1.5 over square root of m, then we can just go ahead and calculate the range where it is. So this is t equals 5, 6, 7, 8. So for 8, if you have a million values, your range where you're going to get a reasonable estimate is really large, and so that gives us something to work with. So, for example, my 1 million entry weblog, I can say, well, how accurate an answer do I want? Well, I want it to be like 95% sure to be within 10%. So that tells us what value for M to use. Okay, let her in. I have a puppy.
He's in the other yard.
Oh, no.
Yeah.
My dog just got out, so oh boy. Maybe can I take a 2-minute break here?
Yes, sure. Yes.
I've got to go find the
Okay.
dog.
Okay.
I'll be right back. What we want, an accurate answer. Now, then we can run experiments. Again, same way, and we get validation of the mathematical model, same way as before. Now, the thing about this algorithm is it's not a streaming algorithm because you have to have the estimate of how many distinct values that you have, and that's not going to work for an unbounded stream. So it has to be adjusted, and so what we want to do is eliminate the need to provide that value of t. And a really simple idea that I came up with when doing a survey talk on Flageolet's algorithms almost 10 years ago now is to make that a variable and increment it as needed. And so my idea then was start at t equals 1, maintain a second sketch for t plus 1. So if we're at looking for more than 8 trailing ones, we also look for 9 so that we can I said when the sketches say half full, increment t, and then reset from the other sketch and set the other one to 0, and then try to estimate the error. And this, I coded this up and it pretty much worked. And I was amazed that such a simple algorithm would work. But I didn't have a model that proved this. And there's a lot of parameters kind of hidden in here. So why half full? Why not quarter full or three-quarters full or whatever? Why increment by one? And setting the second sketch to 0 is forgetting what happened in the past. Isn't that a problem? I thought that we could have a model for that. And for 8 years, I guess, trying to come up with different models. And Svante would say, nope, that one doesn't work. So I never had a proof, never had a model, let alone an explicit form for the bias and the standard error for this kind of algorithm. And I could show, I gave some talks saying, well, I almost have a model. This one really seems to work. But I was flying blind because I actually didn't have analysis. It wasn't until I actually was testing out the thing for different values of t, and I said, well, I'm just going to put in a big value of t, and boom, the thing worked great. And I sent that to Svante, and he said, oh yeah, I think we can analyze this one, and he came up with the analysis that I presented. With that analysis that I just talked about, we can actually answer all these questions.
Yeah.
So,
Sorry, Bob, a question.
yeah.
When you say, I didn't have a model, do you mean that you had a model, but it was not possible to make a rigorous analysis of it?
Right, right.
Okay.
But I was just fooling around. Right?
Yeah.
I admit now.
Difficult to analyze. Okay, I see.
Yeah, and proving that it's normal. I mean, it seemed like normal, and actually, what I needed to know not only that it's normal, I needed to know the constant in order to be able to compare it with other algorithms. So this is hyper-bit-bit. This is with two sketches, and it shows what to do in these two cases. We increment by 4 instead of 1. And we wait till the sketch is almost full, like 98.8% full. And all of this is easy to compute, and that's hyper-bit-bit. And how do we get to these two values? These three things? Well, the analysis gives it to it immediately. So the first one is how much to increment t. So if we have the sketch for t, our estimate for the fraction of zeros in the sketch is m2 to t log 1 over beta. And if we want t plus I, then it's just solve 2t plus I log 1 over beta I, whatever that would be. So you can solve that for beta of I, and this tells us that when the sketch is 97% ones or 3% zeros, then the one for t plus 4 will already be 80% zeros, and for t plus 8, it'll be almost all zeros. So the sketch for t is 97% ones, or only 3% zeros, and the sketch for t plus 8 is nearly all zeros. So what that means is that we can assume that it's all zeros, and then it's just like hyperbit t. The analysis that we gave applies throughout the whole thing, which is an amazing thing to know. And now when to increment t? Well, you just do the math. When the standard error for t plus 4 would be equal to the standard error for t, that's the time to increment t. And that turns out to be, what it is, 0.988. And then the reported cardinality count and also the standard error is just what the analysis for the simple algorithm was. So the analysis applies throughout. It's kind of amazing to realize that. So we're not ignoring any history. Now, it's possible that there are a few ones that we're ignoring, but the hypothesis is the effect of those is negligible, and we test that. So again, I've showed the plot, but it'd be the same. So now we have what we need to compare to other algorithms. So you have to compare in terms of bits of memory. So we're only using 1 bit per item. The other algorithms are using 8 or 64. But anyway, we can the number of streams and the relative error, we can calculate the whole thing. So hyperlog log uses m bytes, but you have to take the square root of b into consideration. Hyperbit t, the standard error is 1.32, and hyperbit bit it's 2.06 over the square root of m star. So it definitely is better. But we can do the math. Now, one problem for hyperbit bit is m is large, which sometimes they want m to be large to be accurate. There's too many zeros in that t plus 8 sketch, so you want to go to hyperbit bit bit. And the problem with that, it uses more memory, and so that's going to affect the trade-offs that I just gave. You don't want to use more memory. But there's an easy way to fix it, actually, because you can encode these sketches in 2-bit values. Because if there's a 1 in the sketch for t plus 8, there's going to be a 1 in the one for t plus 4 and for t too. And so actually, you can get a 2-bit value between 0 and 3 that you can recover all these sketches from. And this gets back to the computer science. It's amazingly fun and easy to actually compute these with bitwise operations, but that's for computer scientists, not for this gang. For here, the point is that we can get the effect of hyper bit with just 2m bits, which means the thing works for large M. So it's a great exercise in hacking, but that's not for this crowd. So again, given m star bits, what accuracy do you expect? Well, again, here's the table, and hyper 2 bits is definitely more accurate for a given number of bits, or how much memory do you need to achieve a given accuracy, and the bottom line is that you get the same accuracy as hyperlog, but half the memory. So that's the bottom line practical, but it's all made possible by the mathematical model that has been tested. I think there still might be a hyperbit out there where you just use 1 bit. I'll still fight on that because there are some choices that seem to test well empirically. So maybe there is a model to cover what happens when you reset the thing, but I don't know. I'll call it still open, but I think it's going to be tough to beat what we have. So again, this is just a summary. We start with a program. We built a mathematical model. We use that to give a hypothesis about performance in the real world, and we ran experiments to get back to the program. And I think that's my talk. Yep. Thank you. Any questions?
Okay, merci. Your questions?
Maybe a small question. How the randomness is introduced in the analysis of algorithms? How we can show the distribution of the randomness in this thing?
We make a very simple assumption that the hash function returns every value with equal probability.
Okay.
Every possible value with equal probability. That's some would consider that's a very unrealistic assumption. But even so, our most famous application of this is an algorithm called linear probing, which Knuth analyzed in the 60s, and that led him to write his books. But if you look at the assumptions he made to do that analysis, they're very, each bit is independently random. They're very strict. My thought on it is you do whatever you need to do to be able to prove rigorously your mathematical model. And then in the real world, we have to assume that we have a hash function that the difference between our hash function and your assumption is not noticeable in the real world. And that has proven to be true in many, many instances.
So we have some algorithms. You introduce some hypothesis, and you construct your mathematical model. And after you approve this model using the application, using the
Well, the idea is that the model has the parameters and it helps you set the values of the parameters. Without that, you're just guessing.
Okay.
And that's what I did for many, many. I ran my algorithm. I'd say, okay, that's 0.794, but it's awfully difficult to go to Amazon and say, try this, it'll probably work. I don't know why. I feel a lot more comfortable saying, it's Euler's constant, and it'll work for you.
I don't know which one they will believe the most. A very fascinating exponential of minus Euler constant or some 0.93. But about the hash function and so on, isn't it what you said? The Mersenne twister is handling this, no?
That's just the one we use. I believe that a simple linear congruential will work fine for this.
Yeah.
I haven't run that experiment, but Jeremy gets too upset when I do it.
But the question is a little bit similar. Can we have a random generator, a uniform random generator in any programming system? So
Yeah, I'm sure that all the big companies that I talk about, I use a different one, right? So definitely, you wouldn't want to have it be dependent on which generator was used. Absolutely. I'll run some experiments with linear congruential just to shut Jeremy up, but there's no way you can prove anything about that. How random is it compared to? I don't know.
And also to sell a little bit more what you say that, okay, it's nice to have the analysis, and in fact, an algorithm is nothing with its analysis. So you said that the initial idea of Martin Hanson, you can always try to do some benchmark and then to try to optimize the constant benchmark after benchmark. But you will have always the question, if you use another size of data, what will be the optimal value? You are never sure. Now you have the proof, and also with your new algorithm, you have the proof, and it squares for any size of
Yeah.
stuff. So
and this goes back like to quicksort, even or what's the cutoff for small values? And there you can find the minimum of the function and use that. And guess what? That's what works in practice. I mean, that was 65 years ago. So.
Something which was a little bit surprising for me, I was not really expecting Gaussian because for me, this, for example, the trailing ones, it's quite similar in flavor to the carry propagation, which was analyzed by Knuth and so on. And because of this, I am more expecting a Gumbel distribution, this double exponential limit law as a stuff. So do you have a little bit an intuition of why it is Gaussian here and not Gumbel?
No, not at all. I mean, no, I don't have intuition on that. For me, it was a hope. So I was running experiments and, try to curve fit to a Gaussian or wherever, or ask AI, is this Gaussian? And to have Svante said, "Oh yeah, it's Gaussian," and not only that, here's the explicit expression for the standard error. That was really a breakthrough.
You have used the word estimators every time in your talk. What kinds of estimator you use? For example, the estimator of n over m. How you estimate this parameter, for example? by the
Well,
average or something else?
uh, the different algorithms do different averages. So,
Okay.
but our last is not. It's just we compute a value, and that's our estimate.
Mhm.
It's not an estimator in statistical sense at all.
Okay. Okay. And in slide 18, you say that the oscillation
Yeah,
is around 10 over minus 6. It has proven that it has this.
that's you just compute the values of the gamma function at those,
Okay.
and it gets really small.
Okay. Okay. Not a simulation. Okay. Okay.
Yeah.
Mm.
I first had a function like this in one of my first papers in the late 70s. And to figure out how to evaluate the gamma function in those times was not easy. Let me see. It wasn't like there were no like packages where you could get it. This was, uh, you know, compute by hand, the way Euler did it. You get the asymptotic formula, and it was a different world.
Mm.
I think sometimes it's good to go back to that world. When I talk about this stuff to computer scientists, I explain to them about my first job, which was on an 8K, 18-bit computer. And you had to put your programs in with switches. You had to physically touch every bit. So when you're physically touching every bit, you really care about the number of bits that you're using. But I think these network switches, they're kind of like that. I mean,
Mm.
they're trying to make those things as small and quick as possible. This program in machine language is probably less than 20 lines, which is amazing. That the combination of that and you need the gamma function in Euler and a lot of the machinery of Poissonization and so forth to really get there.
But Bob, you were mentioning that you had in your young days this nice formula involving some oscillating phenomena. But isn't it there that there is this anecdote that it is because of such a formula that you first met Philippe Lajolet and he came to
Exactly.
you?
We had the same
So,
one
so he came to you.
for a different problem. Yeah.
Ah, it was not for the same problem. Okay.
No. His was a property of trees, evaluating expressions on trees, and mine was Batcher's sorting networks. Uh, and but it's similar kind of sum, after and that's there's our papers in the 80s and 90s showed that lots and lots of problems that boil down to this same thing, simply because the combinatorial models are very similar. And after you do the asymptotics, you come up to summing this 1 minus e to the minus n over whatever, it comes out similar.
Yes,
So we
no, with
recognize
Mini
it when we
transform, we
see it.
understand it. Yes. Mhm.
Yeah.
And you mentioned trees. So about trees, I have one question. So in some of your first slides, you had some background image, and I think that I have a guess that
Yes,
maybe
that's it.
I don't know if people will see it, but there is a kind of
Yeah.
there is a kind of tree here. And in fact, I don't know what is the story behind this. So can you explain this? I
Oh,
think I never heard.
no, that's just a layout of a random tree. I think where you just put all the nodes centered on the center line and then draw the edges as appropriate. Uh, let's see, I have one here. Just a second. These
Yeah.
are random maps. Let's see. Oh, it's not focusing.
AI is good for faces, but I think that you have something
Yeah,
to
that's
make
funny.
the face of the tree blurry.
Yeah,
But
so
okay.
it's just a way that Philippe came up with for plotting random trees.
Mhm.
And it's simple. Uh,
And And by the way, I have also this one, so I don't know if you ever saw it,
Yes,
because
I
it
had
is
that.
the French version of your first book with Philippe, the French version.
By the way, I wish that I had called this book, or that we had called this book, Mathematical Methods for Algorithm Science.
Ah, it works well, yes. I
Yeah.
agree, I understand.
I wish that I had thought of the term algorithm science a long time ago. I
Uh-huh.
wish Knut had thought of it.
Yeah,
It really does.
yeah, it's really
Really does
it's
express
true.
what he does.
Mhm. Okay. Is there some question in the room? More questions, feedback, questions, whatever? Improvement for hyper bit algorithms?
And I'll send the slides along right when we're done.
Yeah. So thanks, because it's a very wonderful success story for the analysis of algorithms. I
Yep.
think it's a really interplay between really programming and so on, and also who went to private companies. So
Yep.
I did the joke in the chat that can we ask some funding to those companies because they are using our nice
Yeah, I
algorithm.
know. Because we're not getting it from the government anymore. So. We actually had heard from a